All right, welcome back to the new week. They're passing by quickly, that's for sure. So we have started programming Gaussian elimination, or rather its first step last time. So let's say that I have an example 3x3 system that is always going to be the sort of the simplest system that I'm going to work with. The procedure that we follow in Gaussian elimination first goes through so-called forward elimination. So I basically go pivot element by pivot element. So this is my first pivot element. And assuming it's not zero, then I can use it to eliminate these two elements in the column below. Okay? So basically, I multiply with the appropriate coefficient, my first row, and add it to the second row so that this element zeroes out. Right? And all other elements, they just change accordingly. And we know already that basically that if I have a system of linear equation, I can take a linear combination of the two equations and replace one of them with that linear combination without really changing the solution to this system. Great. And then I proceed and do that for all of the elements in this column. And we kind of went through the step-by-step procedure programming that last time. And then after that, so once I do that, this is basically, we multiply row 1 by A21, A11 and subtract from row 2, or the other way around. I can just I can either do this row minus this one, right? Minus that coefficient times the first one, or that same thing just multiplied by -1, it doesn't really matter. And then, as long as I'm doing it consistently and programming it consistently, and then I multiply row 1 by A31 over A11 and subtract from row 3. And that way I zero out these two. And these are my new elements that have changed in the process. And then this becomes my pivot element. Okay? And this pivot element needs to be non-zero. Otherwise, I have to flip the rows. And then I use that element to basically eliminate this one. So after that, I should have triangular system, upper triangular system with zeros below the diagonal. And then I can actually start solving it. So if I had a triangular system, let me come up with this one here as an example. Then I know immediately how to solve for the last element. In this case, the third one. So I can immediately solve for this last, if I'm calling it x3. 4x3 is equal to 8, so my x3 is equal to 8 over 4, which is 2. Right? Then I can use the knowledge that I have gained into my equation above. So now I have that 3x2 minus 2 times 2 is equal to -1. So basically I can calculate x2. And finally, I put both x3 and x2 into this first equation and solve for x1. This is great when we are doing on paper, right? So now question is, how do I program computer to do so consistently? Okay. The writing a line that basically solve for this last one is easy, right? But then after that, okay, basically I have this diagonal element, and then all of the others afterwards I know, and I need to put on the right-hand side in an equation. And that's essentially what is done here. So this is my last element, okay? And then everyone, so for all of the others, basically I start xi is my bi, which is what I had on the right-hand side, minus some of the preceding elements that I have, or the ones that used to be on the left-hand side, multiplied with the appropriate coefficients, and divided by this diagonal element AII. Is this going way over the head? Shall we break it down? Let's break it down. All right. So let's break it down in the program, but this is where technically this is one of those sums that we used to practice our for loops on. So you're going to get that chance. But let's actually see how I got to that sum. All right, where is my program? I will find and basically continue where we left off on Friday. 310 lectures, Spring, Python code. Where's my last?
Did you see it?
That's a great question because my computer rebooted, so I don't think it got saved.
It was entitled Lecture6 Solving Linear System Gaussian Elimination.
Yes, except that that's not what my computer thinks.
Here it is. Oh, I saw it.
No, that's from last semester. Is it here somewhere? 3 days ago. Okay, I saved it in the wrong directory. All good, did not lose it. I was like, yeah, I remember naming it, so therefore it should have been saved somewhere. All right, so this is the step by step, just as a quick review. So I have my A and B, which I use for practice. And then this is my forward elimination step. So this required essentially a nested for loop. So for every pivot element, this is my diagonal element that should be non-zero. Right now I'm not doing anything in case it is 0. I'm just saying please program partial pivoting, which you will do for your homework. So essentially, if this is a non-zero element, then I can actually use it to eliminate all of the elements below. So this is the coefficient that I am multiplying my ith row with, and then my jth row for all these j's below becomes this coefficient times ith row. This is a way to take ith row from matrix A plus jth row. And I also have to modify B. I should not forget to do that.
Do you have this uploaded?
I don't. Would that help right now?
It would, because I didn't get that.
All right, so let's actually just do that quickly. Ba-bum. So files, I'm going to do it in files, code, upload. This one. There we go. Should be there in a few seconds. So if you didn't get that, then you can start from here. Now let's go and kind of work again step by step. So now, in this case, I'm going to re-execute this once again so that and I have an error because to be complete, this should import NumPy. There we go. So now my A is indeed upper triangular, and this is my changed B. So essentially, the way I would solve for this is that my last element, minus 2 times x3, or in Python language it will be x2 because I have x0, x1, x2, It's going to be equal to 2, which is my b of 2, right? So here's how I'm going to do this. First, I want to get x. This is computer. Computer doesn't know anything about my solution x just yet. We have just changed matrix A and B. So first I'm going to do, first thing I'm going to do is I'm going to allocate memory. So it's NP array or NP zeros of the same size as B shape. Okay. So now I just have it in my memory. So this is just allocating memory for solution. So if I were solving this by hand, I would say, okay, I have x0, x1, x2 to find. My last one, x of 2, is b of 2 divided by a of 2, 2. Is that correct? Do we agree? This is my upper triangular matrix. Imagine this B is actually flipped over. Python doesn't really do 1 by 3, 3 by 1 business. It's all one-dimensional arrays. Yes? Okay. So I'm going to generalize this. I'm going to do here generalize immediately. So if I remember, n by n is my system, right? So in terms of using n, which is size of the system, how would I express this so that it's more general for any matrix of size n?
X of n.
X of n minus 1, right? Yeah? So I'm going to copy that. And I'm going to generalize it and say, well, this last one is always x of n minus 1 if my matrix is n by n, correct? Okay. Cool. So I at least got that. Now, if I was solving by hand, I know that I would have the equation here, minus 2, okay? Technically, my equation is minus 2 is a of 1, 1, correct? Times x of 1 plus a of, what is 5? A of 1, 2, if I'm starting from 0, times x of 2. That's equal on the right hand side to what? B of? This is my A, this is my B. B of 1, correct? And I have a 0 leading a 0, so I don't need to work with x of 0, correct? That's my equation, where I'm trying to recover x of 1 from. Yes? So technically, my x of 1 is equal to b of 1 minus a of 1, 1 times x of 1. All of that divided by a of 2, 2. No, a of 1, 1, and this was 1, 2. And nobody's saying anything. I'm typing up error after error. Yes? This is just algebra. And maybe I should print it. Print x of 2. Well, it's a nice number, so hopefully I did things correctly. I didn't get like 2.3, so 7 of 8, 1, 2, and so forth. Yeah? Yes? Fine. Now you all type in by hand x of 2. Assuming you have this upper triangular system. But use A and B, so this could technically work for any 3 by 3 matrix A and B, right?
Do you mean x of 2 or x of 0?
X of 0. I was testing you. You should get minus 1, 2, and 2. So this solution that I call solving by hand basically works for any matrix that is 3 by 3 and vector B 3 by 1 that you type in and that doesn't require partial pivoting. Do we agree? Well, that's useful, but not so much because I'd like to solve larger systems. So I have to recognize a pattern here and try to generalize the solution. Okay. So what do I have here? X of 2 is my n minus 1. Then I go to n minus 2 element, which is right above, right? Which is right here, x of 1, okay? And that one will have corresponding b, yes? Minus this x of 2 that I just computed, which is my x on n minus 1, and corresponding element of A. Yes? So all of the previously computed x's play a role here, which is only 1 right now, and then I divide by this diagonal element A of 1, 1. Then once I compute this, okay, I have 2 of them computed, and I add them up, sort of a linear combination of them with the corresponding elements in that same row of A. So that's this sum here. So B corresponds for x of 0, I take B corresponding B minus this A times computed x plus the second A times computed x, and then I divide by a diagonal element. So if I was writing a rule, I'm going to say that there's this sum. This sum is going to go for all i's in what range?
N-1.
So n minus 1 is already done. So n minus 2, I start from n minus 2, right? And go all the way to 0, except that weird rule that 0, in order to hit it, have to say 1 less. And I'm going to step by minus 1, right? That's the range of x's. So I go from n minus 2 all the way to 0. And to get a 0, I have to have something that is less than 0 here. Okay. So technically, my x of I, and I'm going to literally write it this way. So x of I is b of I minus, I'm going to call it sum. And sum is probably a function, well, sum is, should be fine. Sum, and divided by A of I. And now I just have to compute this sum, right? Do you see what I'm doing here? So mentally, I'm breaking down this to a smaller and smaller problem, and I write down what I know. It's some sort of a sum, okay? And sum involves all of the previous elements, yes? That I already computed so far. So, well, if I'm computing a sum, there's another thing I know. I got to initialize with 0. So write down what you know as you go. And you'll be surprised how actually little by little you get to figuring this out. So this sum involves this basically, sum involves all previously computed x's, elements of x. So it's going to be a for loop. I'm going to call it a j in range. Now I have to figure out the range. So if I am element of like I'm at ith x that I'm trying to compute, all of the previous, since I went backwards, all of the previous ones are I plus 1, I plus 2, all the way to n minus 1. Is that correct? So, and again, I'm going to write this down as a mental note. So basically all, so elements are I plus 1, I plus 2, and all the way to n minus 1, which is that last one, element of x. So let me write down then the range that gives me that. Yeah? So what am I adding to this sum? some sort of element of I, to be decided which one, times this x of j. So this sort of a summation element like this, that is in the same row as the x that I'm currently computing. And to correspond to x of j, it has to be in the jth column. Do we see a pattern? So for my x of j, I have a of I, j times x of j. Then my j changes. So this is still j, but this is still a of I, j, x of j. So keep adding as many as I have of those. That's it. So it's not a lot of code, but you have to kind of break it down and generalize as you go. Make a few mistakes and then fix them. Oh well. I don't think I made a mistake. We're gonna find it. We're gonna find out in a moment. Moment of truth. Which area am I gonna get?
You didn't return anything and you have X.
There's no function, so I don't need to return. I didn't write a function. I'm just computing as I go. That's our next step, is to write a function. I agree. Okay, we got the same result. So is it mentally clear what I did here? Piece of paper sometimes is always helpful to figuring out patterns. Obviously, I've done this a couple of times so far, so I'm a little faster. So don't be intimidated by that. But you kind of just have to figure out where's the pattern. You can see kind of the pattern is there. You just have to nail it down what it is.
Where do you initialize n?
In this previous, I had it. N is, but yes, it's the size of the system. If you want to reinitialize it, you can do it. So this is my back substitution. So this solving by hand works for a 3x3 system. And this is generalized for any system of size n by n. And this is code for back substitution.
For the I range, why is it n minus 2?
Because n minus 1 I already computed. That said, let's see if I can just actually write n minus 1. If I do, this sum will be 0, and then there will be nothing here to do. Because if I'm n minus 1, range of n is empty. So this loop will not execute, and then I will have that x of I is b of I minus 0 divided by a of I, which works, which will give me precisely this. Yeah? So either way, okay, so technically I can take this away, because when I put n minus 1, this still works. But that's what I would call that you would get to that on your second iteration through the code. It's easier to write something you know first and then start initialize from that. But then to have a cleaner code, you would on the second loop just remove this first line and start from n minus 1. Is everybody following what I'm saying? So I initialize. I always have to initialize. Whatever it is that you do, you gotta initialize. I gotta allocate memory for x because my computer is not smart enough to see it coming. Computer doesn't know what to do until I tell it. And then I start from the first one, first element that I know, and I work down. But once I actually write this down, I can see that even if I write n-1 here, this for loop will not execute at all because the range will be from n to n. That's an empty range. Okay? And if it's an empty range, for loop will simply not execute. It's not an error to not have it. This sum is then 0, so you will have here x of n-1 is b of n-1 minus 0 divided by a on n-1, n-1, which is the same line as this. So I don't have to have this line if I just write here n-1. And I have technically a cleaner code. Less writing, right? It's all good. Yes? So are we okay with this change? Or I can just revert it to what I wrote. Both things work. Didn't speed it up, didn't do anything. Huh? Yes?
I have a question about, so when you allocated memory by using a matrix of zeros, is that more popular than using just like appending a matrix? Or like appending a vector over and over?
So if you append the vector over and over, there's a cost to it. There's a cost to calling a function. So you would, let's say that you have 1,000 of these, you would call append 1,000 times. There's an overhead to it, like making a phone call. Okay? So essentially, you make one phone call to zeros, get it all done, you have that memory. There's a cost to it as follows. Initially, when you just have one element, well, it allocated space on a bookshelf for one book. Then you come in and like, no, I need space for 2 books. No, I need space for 3 books. And then it suddenly starts realizing that in that portion of memory, it doesn't have space for 3 books, and it has to find it elsewhere. That's why there's more cost to it. Whereas if initially you know you need space for 3 books, ask for 3 books immediately. Okay? So when allocating memory, and normally in small problems you will not see a difference whatsoever. But we will actually have an exercise of pushing the limits, and we have this sizable chunks of memory, then it starts being expensive. Because normally when I'm operating with one array, it's going to patch it up. It's going to figure it out. It's just going to be slower at doing so. So there's something in your computers. Sometimes maybe your computer system analyst or somebody will ask you to do disk defragmentation, which is actually cleaning up these memory issues, like where you had a growing piece of memory that then suddenly got sent in various locations. And it's more efficient to put that up on one bookshelf, so to speak. And all of this, and that happens when, let's say that you're working on a project over the entire semester, the file that you're working with is growing, and that could possibly grow. So you can actually do a cleanup on your computer called disk defragmentation that will clean up this appending the memory as you go, right? So it is more efficient. I'm going to write that as a code, as a general tip that you should stick to. If you know the size of the array you will need, allocate it immediately. This is more efficient than appending an array as you go.
And it's because we're using a discrete data set, we're always going to know the shape.
Well, if you're solving your A and B, it's determined by the size of A and B. That's it. So in this case, you know. So now if I had a problem, so somebody said that let's create a function. So I want you to now put together a function, Gaussian elimination, that will have both of these pieces, both forward elimination and backward substitution in there. then this function should take any A and B as an input, not just this given one. Okay? This is your test, so it shouldn't be part of the code. Okay? And figure out the size of the system, and then solve it and return X. Okay? So take a moment to create a function, Gaussian elimination, that takes any A, B as input and returns solution X to AX is equal to B using above forward elimination and back substitution steps. Don't forget to clean up indentation as you copy the code into a function. Did everybody get to exercise and cut, copy, paste, and then indent to be in the indent by 4 because it's in the block of this function. Indentation error, of course.
I indented everything.
No.
Just maybe
This
indented again.
needs, yeah, that's the part of this forward, right? So this entire block from sum to. not delete. Delete and indent are very different. Questions? Mm-hmm.
So our output is x1, x2, x3, essentially, like our three solutions.
Yes, but I did actually put them in an array.
Right.
So output is an array. Okay. Now, if I was solving this by hand, I would think of it as a column, right? Except that Python doesn't do columns for 1D array. It says it's all 1D. Okay. So just as a quick review of what have we done here. So basically this is that same rule that we implemented in back substitution, put together as a sum, oddly looking sum. So the sum goes from I plus 1 to the size of the array. Okay. So we have written this Python code. So just as a review, one thing that we didn't program here is what happens if I have a 0 as a pivot element. You will modify the code to do that in your homework that is going to be assigned today. And you could also pivot columns, which is what we're not going to do here. In your homework, you will also see what happens, what's a pitfall with the round of errors. So in Gaussian elimination, we have a lot of things to do, especially as the problems get large. Okay? And round of error can seriously pile up with all of these summations and additions and calculation. Okay? And typically we use this for problems that are on the order of few hundred equations, but not more. And especially if I have this A matrix that is close to not having an inverse or not being invertible, that can actually cause, it's a so-called ill-conditioned system that can cause a lot of trouble. Okay? Now, this partial pivoting, you will basically get to switch two rows that are problematic for your homework. That doesn't change any solution, so you should be still able to get that as a correct solution. We will not go into full pivoting, but it works similarly. Now, one exercise that I will ask you to do is to test the Gaussian elimination function that you have just created on problems of increasing size, just to see how timing works here. And we will test two things. So we will take systems of n is 1,000, 2,000, or 5,000, and you will create a random matrix A of that size, as well as a random vector of that size. Just some random numbers, okay? And you will call np_random.rand to do that. And then we will time it, and this is how you will time it. This is in your slides, and slides have been posted. Then you will time it to see how long it takes. I will send you a form where you will enter your result, just to see across the different computers that we are using in this class how fast this takes. Make sure, especially in this last case of 5,000, to leave your computer going for an hour, 2 hours, 3 hours, depending on your heart rate. Just to see. And 5,000 in reservoir simulation, just by the way, is nothing. It's a good day. Even 1 million by 1 million is a good day. Okay? So just to see how expensive this can be. And we will also test it against numpy.linalg.solve. This is basically the functions, selected numpy functions. So this solver will basically solve a linear matrix equation. Now this is a piece of code, so we don't know what it's going to use. Probably one of the indirect methods that we're dealing with later. Okay, so it's going to use something faster than Gaussian elimination, but just to show you how fast or not fast things get compared to the code that we programmed. So just to give you an idea, this is the timing Gaussian elimination actually on a computer that predates this one. This one might be actually slower, so I don't know. So this was tested on my previous MacBook, and basically as I went to almost 8,000, this is in seconds. How many hours is 16,000 seconds? 1 hour has 3,600 seconds, right? So almost 4 hours. Now your linalg.solve will perform much better, and you will see the comparison. Okay? So we will then next time comment on this just to see what the class, we will see what, I will send you a form where to enter the results. And just to play with that and to understand that when you don't program things smartly, they can take a lot of time. And then we will comment on how we go. Okay? All right. I see you on Wednesday.